Gravity does not pull you down. The geometry of curved spacetime. Right now, satellites orbiting Earth are running atomic clocks, incredibly precise timepieces that tick with almost perfect regularity. But there's something strange. The clocks on satellites tick slightly faster than identical clocks on the ground. Not by much, about 38 microseconds per day. But the difference is real and measurable. This isn't a malfunction. It's not interference or calibration error. It's gravity. Time itself runs at different rates depending on where you are in a gravitational field. Clocks higher up, farther from Earth's center, run faster than clocks closer to the surface. If we didn't account for this effect, the global positioning system would accumulate errors of several kilometers per day. GPS only works because we correct for the fact that gravity warps time. But here's the question that should bother you. How does gravity warp time? What does that even mean? And if gravity can affect clocks, what else is it affecting that we don't notice? The answer, according to Einstein, is everything. Gravity isn't a force pulling you toward Earth. It's not an invisible tug acting across space. Gravity is the shape of space-time itself. And everything you experience as weight, as falling, as orbiting, is actually the result of moving through geometry. Let's figure out what that means. Newton's picture. For more than 2 centuries, gravity was understood through Isaac Newton's framework. Newton described gravity as a force. Every object with mass attracts every other object with mass. The strength of the attraction depends on how massive the objects are and how far apart they are. Double the distance, and the force becomes 4 times weaker. The inverse square law. This framework works remarkably well. It predicts planetary orbits. It explains tides. It lets us calculate trajectories for spacecraft and predict eclipses centuries in advance. But Newton himself was uncomfortable with one aspect of his theory. How does gravity act across empty space? How does Earth know the moon is there and pull on it? How does the sun reach across millions of kilometers to hold the planets in orbit? Newton called this action at a distance. He admitted he had no mechanism for it. He could describe how gravity behaved mathematically, but not what gravity actually was or how it operated. For practical purposes, this didn't matter. The equations worked. Predictions matched observations. That was enough. But there was a deeper puzzle lurking in Newton's theory. One that seemed like a coincidence, but turned out to be a profound clue. In Newton's framework, there are 2 kinds of mass. Inertial mass, which measures how hard it is to accelerate an object, and gravitational mass, which measures how strongly an object responds to gravity. These seem like different properties. Inertia is about resistance to changing motion. Gravity is about attraction between objects. There's no obvious reason they should be related. But experiments show they're identical. A bowling ball and a feather, if you drop them in a vacuum, accelerate downward at exactly the same rate. The bowling ball has more gravitational mass, so gravity pulls harder on it. But it also has more inertial mass, so it resists acceleration more. The 2 effects exactly cancel. This equality holds to extraordinary precision, better than 1 part in a trillion. It's not approximate, it's exact. Why? Newton had no answer. It was just a fact about the universe, mysterious but useful. Einstein realized this equality was the key to understanding what gravity really is. Equivalence and free fall. Einstein's insight came from thinking about acceleration and gravity together. Imagine you're in a windowless laboratory module, deep in space, far from any planets or stars. You float freely inside. Objects don't fall. There's no up or down. This is what zero gravity feels like. Now imagine the module starts accelerating. Rockets fire underneath, pushing the entire structure upward at a steady rate. Suddenly, you feel pressed against the floor. Objects that were floating fall downward. If you drop a ball, it accelerates toward the floor. From inside the module, this feels exactly like gravity. You can't tell without looking outside, whether you're accelerating through space or sitting stationary on the surface of a planet. This is the equivalence principle. Acceleration and gravity produce identical effects locally. If you're in a small enough region of space for a short enough time, there's no experiment you can do to distinguish between them. Now flip the scenario. You're standing on Earth's surface. You feel weight. The ground presses up against your feet. Everything about your experience suggests gravity is pulling you downward. But what if gravity isn't pulling you at all? What if you're accelerating upward, and gravity is just preventing you from following your natural path? Consider free fall. Jump off a diving board. For the brief moments before you hit the water, you feel weightless. Your stomach lifts. You float relative to objects falling with you. This isn't because gravity stopped acting on you. Earth's gravitational field is exactly as strong in the air as it is on the ground. You feel weightless because nothing is pushing on you. No contact forces, no support. You're in free fall, and free fall is the natural state of motion in a gravitational field. When you're standing on the ground is pushing up on you. It's preventing you from falling. That push, that contact force, is what you experience as weight. Weight is not gravity pulling down. Weight is the ground pushing up. This sounds absurd at first. How can the ground be pushing you upward when you're standing still? The answer requires rethinking what standing still means, and that requires understanding curved spacetime. Geodesics and curved spacetime. Here's a question. What's the shortest route between two cities on opposite sides of Earth? You might think a straight line, but you can't travel in a straight line on the surface of a sphere without burrowing through the planet. If you're constrained to the surface, the shortest route is a curve. Specifically, it's a segment of a great circle, the largest possible circle you can draw on the sphere. This is why long-distance airline flights follow curved paths when you plot them on a flat map. The map distorts the geometry. What looks curved on the flat map is actually the straightest possible path on the curved surface of Earth. Geodesics are the generalization of straight lines to curved spaces. They're the paths that are as straight as possible given the geometry you're working in. Now extend this idea to spacetime. Spacetime is the four-dimensional combination of space and time. Every event, every moment at every location is a point in spacetime. Your entire history, from birth to death, is a curve through spacetime called a world line. In flat spacetime, far from any massive objects, geodesics are straight world lines. An object at rest stays at rest. An object in motion continues in a straight line at constant speed. This is Newton's first law. But near massive objects, spacetime is curved. And when spacetime curves, geodesics curve too. An object in free fall is following a geodesic. It's taking the straightest possible path through curved spacetime. From the object's perspective, it's not accelerating. Nothing is pushing or pulling on it. It's moving naturally, the way objects move when no forces act on them. But from the perspective of someone standing on Earth's surface, that freely falling object appears to accelerate downward. It seems to be pulled by gravity. The resolution is that you, standing on the ground, are not following a geodesic. The ground is pushing you upward, off the natural path you would follow if you were in free fall. You're accelerating upward through curved spacetime, even though your spatial position isn't changing. This is why you feel weight. The ground exerts a force on you. That force produces proper acceleration, the kind of acceleration you can feel, the kind measured by an accelerometer. And proper acceleration is what creates the sensation of weight. In free fall, your proper acceleration is zero. You're weightless. You're following a geodesic through spacetime, which is the natural, unforced motion. On the ground, your proper acceleration points upward. You're being pushed off your geodesic, and that push is what you interpret as weight, as gravity pulling you down. But nothing is pulling. You're being pushed. And the reason that push is necessary is because spacetime is curved, and your geodesic points downward through that curve. evidence, and the ISS. This picture of gravity as curved spacetime isn't just philosophy. It makes testable predictions that differ from Newton's theory. We've already mentioned one. Gravitational time dilation. Clocks run at different rates depending on the strength of the gravitational field. Deeper in the field, time runs slower. Higher up, time runs faster. This is not a property of the clocks. It's a property of time itself. Every physical process runs slower in a stronger gravitational field. Atomic vibrations, chemical reactions, biological aging. Time is not absolute. It's affected by gravity, by the curvature of spacetime. Another prediction is gravitational lensing. Light travels in straight lines through flat spacetime, but in curved spacetime, light follows geodesics, which means light paths bend near massive objects. This was confirmed spectacularly during a solar eclipse in 1919. Arthur Eddington measured the positions of stars that appeared near the Sun during the eclipse. The stars were slightly displaced from their usual positions because the Sun's gravity bent the light traveling from those stars to Earth. This effect is now used routinely in astronomy. Massive galaxy clusters act as gravitational lenses, bending light from more distant galaxies behind them. Sometimes this creates multiple images of the same background galaxy or distorts the galaxy into arcs and rings. We use these distortions to map the distribution of mass, including dark matter, in the universe. Einstein's theory also explained a long-standing puzzle about Mercury's orbit. Mercury's elliptical path around the Sun rotates slowly over time. The point of closest approach, the perihelion, shifts by a tiny amount each orbit. Newton's theory predicted most of this shift, but not all of it. There was a discrepancy of 43 arcseconds per century. General relativity predicted exactly this excess. The curvature of spacetime near the Sun affects Mercury's orbit in a way Newton's theory couldn't capture. Einstein called this calculation the happiest moment of his life. More recently, we've detected gravitational waves. These are ripples in spacetime itself, created when massive objects like black holes or neutron stars collide. The waves propagate outward at the speed of light, stretching and squeezing space as they pass. LIGO detected the first gravitational waves in 2015, opening a new way to observe the universe. Now, let's clear up a common misconception about astronauts on the International Space Station. People often say astronauts experience zero gravity. That's misleading. Earth's gravitational field at the altitude of the ISS is about 90% as strong as it is on the surface. Gravity is definitely present. Astronauts float because they're in free fall. The station and everything inside it are falling toward Earth continuously, but they're also moving sideways fast enough that they keep missing Earth. That's what an orbit is. Continuous free fall with enough tangential velocity that you never hit the ground. Everything on the station falls together, following the same geodesic through curved spacetime. Astronauts, equipment, water droplets. They all float relative to each other because they're all in free fall, all moving along geodesics, all experiencing zero proper acceleration. It's not zero gravity, it's free fall. Extremes. Gravity gets more interesting when spacetime curvature becomes extreme. Near a black hole, spacetime is so severely curved that geodesics behave in bizarre ways. At the event horizon, the boundary of the black hole, all future directed paths point inward. If you cross that boundary, every possible way you could move forward in time takes you closer to the center. You can't turn around. You can't hover. You can't escape. Not because something is pulling you with overwhelming force, but because the geometry of spacetime itself has become so warped that all paths lead inward. Time dilation also becomes extreme. Far from a black hole, you could watch someone falling toward it, and you'd see them slow down as they approach the horizon. Their time, from your perspective, would stretch out. They'd appear to freeze just at the edge, taking an infinite amount of your time to cross. But from their perspective, Nothing special happens at the horizon. They cross it in finite time. They continue falling. It's only later, as they approach the center, that tidal forces become destructive. These are not predictions we can test directly with humans, but we can observe black holes indirectly. We see stars orbiting invisible massive objects. We detect X-rays from matter spiraling into black holes. We've even imaged the shadow of a black hole's event horizon using radio telescopes. Every observation confirms Einstein's picture. Gravity is not a force, it's geometry. And that geometry can become arbitrarily curved, creating environments completely unlike anything in our everyday experience. So what have we learned? Gravity is not a force pulling you toward Earth. It's the curvature of space-time around massive objects. When you're in free fall, you're following the natural, unforced path through that curved geometry. You're weightless because nothing is pushing on you. When you're standing on the ground, you feel weight because the ground is pushing you upward, preventing you from falling, forcing you off your geodesic. That push, that proper acceleration, is what creates the sensation we call weight. Newton's theory of gravity is a magnificent approximation. For most purposes, treating gravity as a force works perfectly well. But Einstein's theory reveals the deeper mechanism. Gravity isn't a force transmitted across space. It's the shape of space and time themselves. This isn't just an abstract idea. It affects GPS satellites. It bends light from distant galaxies. It creates gravitational waves. It explains black holes. The curvature of space-time is real and measurable. And it changes how we think about motion, causality, and the structure of the universe. Here's a question to leave you with. If gravity is the curvature of space-time and mass creates that curvature, then what about energy? Energy and mass are related through Einstein's famous equation. Does energy curve space-time too? And if so, what does that imply about light, which has energy but no mass? Think about that. The universe is geometry, and geometry is richer than we imagine.